morning to you all. Welcome into today's session. Today we are going to go through the May-June 2023 variant 63, okay, for the practical or alternative to practical paper, okay. It will be a good thing if you have the paper open in front of you so you can follow easily. The first question says, a student determines the mass MR of a meter ruler by balancing method, okay? He uses the apparatus shown in figure 1.1, and he's showing the balancing apparatus. I think we have seen that before, or you have seen that before. It has a meter ruler, a pivot, and a mass, okay? And he's showing us two lenses. One is A and the other is B. A, if we can see from the image or the figure, it is the distance between the center of mass of the object or the load and the pivot. B is the mass or the distance between the pivot and the center of mass, or the 50 centimeter mark more accurately of the meter ruler, okay? Now, the student places a circle load of mass 20 grams on the meter ruler, but in a position different from that shown in figure 1.1. Determines the distance d naught of the center of mass of the load from the zero end of the ruler, as shown in figure 1.1. It is not to scale. If he's telling you not to scale, meaning that you cannot use your meter ruler to just measure the length, okay? You cannot do that. Now, the way to go, okay, he's asking, where is the center of this object is on the meter ruler. The center, or the reading for the center, it is below the mass, so we cannot see it. It is not easy to see, or it is impossible to see. So the way to do that is to take a reading for this position, the left hand side, take a reading for the right hand side. We have two readings, okay? We can call them anything, L1, and this is L2, anything like this. And the position, okay, this is important, the position is L1 plus L2 divide 2, okay? If we apply this to this case, the reading here is 6 centimeters. Reading from here, it is 9 centimeters. If you can see it, let me zoom in for you to see it much easier. Okay, so this one, the reading on this left side is 6 centimeters. The reading on the right side is 9 centimeters. So it is 6 plus 9 divide 2. It is 7.5 centimeters. So the reading here is 7.5 centimeters. Okay. In some cases, he's not asking about the position of the center of mass. What he is asking is where, or more accurately, the diameter of this shape. He's asking about the diameter of this shape. In this case, we can say the diameter is equal this measurement or this reading minus that reading. That's simple. L2 minus L1. In that case, it is 9 centimeters minus 6 centimeters. Then the diameter of this object is 3 centimeters. Okay? So you better make sure that you understand or you know what he's exactly asking for. Is it the position or is it the diameter? Okay? That's simple. Now, the student places the meter ruler on the pivot and changes the position of the load so that the center of the load is at the 5 centimeter mark. He adjusts the position of the meter ruler in the pivot until the meter ruler is as near as possible to being balanced. Describe a technique for ensuring that the ruler is as near as possible to being balanced. So he's asking us how or the steps that we are going to follow to balance the meter ruler. Okay, this is kind of a recurring question. It comes very often. Okay, and the way to answer it is very simple. You just have to report it like this: slowly and gently move the meter ruler back and forth about the position where the image or the balance is expected till you get the best balance. Okay, this is how you answer this kind of question. Okay, now part 2, the student determines the scale reading P on the ruler as the position of the pivot. He calculates the distance A between the 5 centimeter mark and the pivot, and the distance B between the 5 centimeter mark and the pivot. Okay, so P is the position of the pivot. Okay, the distance A is the distance between the load and the pivot. B is the distance between the pivot and the 50 centimeter mark. Okay, he repeats the procedure for values M is equal 40, 60, 80, and 100. His results are shown in the table. Okay, so now we got A and B. Now he's telling us to calculate B over A. So simply, so it is 5.5 divides 39.5. 5.5 divide 39.5. 0.139. 0.139. He is asking it to be reported to two significant figures. So we can say it is 0.14. Okay. For the value M 20 gram, calculate and record B over A. Okay, we have already done that. Plot a graph of mg on the y-axis against BA on the x-axis. Draw the best fit line. Okay, he is not telling us should we start from 0, 0 or not. Okay, so what he's asking is to plot this is on the x-axis and this on the y-axis. Okay, mg on the y-axis. So picking a scale for the y-axis is quite easy. Okay, it starts from 20 goes to 100. We have here 5 squares, 1, 2, 3, 4, 5. Okay, so it will be a good thing to start from 0, 0, 20, 40, 60, 80, and this is the 100. Okay, if you go to the x scale, it starts from 0.14 goes to 0.67. Okay, so the way to calculate the scale for it, it is maximum minus minimum divided by the number of squares. The maximum here is 0.67 minus 0.14 divided by 5. Let us do the math. 0.67 minus 0.114 is equal, divide 5, you get 0.11. Okay, 0.11, we cannot do that. Okay, the best good scale that we can try, the next best one that we can try is 0.2. Okay, we don't like to use scales like fractions, something like 0.15, 0.18, 0.11. Those are not kind of good scales. So what we are going to pick is 0.2. If we do that, we notice that we can actually start again the x-axis from 0. So it is 0, 0.2, 0.4, 0.6, and 0.8. Okay, we have to label the axis. The y-axis is m grams. This one is b over a, and it doesn't have units. Okay, I have already made or plotted the data points. Okay, here are. If you are in doubt how you can make a good plot or choose a good scale, then you have a video. I have a video, okay, in this series, which you can reference or go back and check, and it will help you make a good choice for scales. Okay, determines the gradient g. Okay, this is the straight line. Now it determines the gradient g of the graph. Show clearly on the graph how you obtain the necessary information. So as you remember, to get the gradient of a straight line, you have to draw a right angle triangle like this one. Okay, like the one you see over here, this one. Okay, we draw a right angle triangle. It's always easier if you write on the graph, or it is actually recommended if you write on the graph the positions where the straight line or the right angle triangle meets with the straight line. Okay, for this point, the x reading for it is 0.6 and the y is 90. For that point, the x reading is 0.6, the y reading for this point is 30. For this point, the x reading is 0.2 and the y reading is 0.30. So the gradient is, as you know, is change in y divided by change in x. So we apply that. So the gradient is the change in y. Change in y is 90 minus 30. The change in x is 0.6 minus 0.2. Okay, if you do the math, you get 105 grams. Okay, so the gradient is 105 grams. The mass mr of the meter ruler is numerically equal to g. Write down the value of mr in this experiment, including the unit. They are both equal. mr is equal to g. Okay, then it is 105 grams. The determination of mr by this method assumes that the center of mass of the meter ruler is exactly at the 50 centimeter mark. Okay, suggest how you would use apparatus from 1.1 to test whether the center of mass of the meter ruler is at the 50 centimeter mark. So The question simply is to check or to find the center of mass of the given meter ruler. So how we do that? If you remember from your physics course, we are going to balance the meter ruler without any load on the pivot. Okay, this is it. This is our meter ruler. Then we are going to balance like this. Okay, we balance it like this. And we say balance, sorry, balance the meter ruler on without any loads on the pivot. The position at which the meter ruler balances is the center of mass. Okay, so balance it without any load, the position where the center of mass is, okay, or the reading of the position of the pivot is going to be the position of the center of mass. A student finds the center of mass of her meter ruler is 48.7, meaning what? The center of mass is a little bit shifted away. Okay, suggest how she changes the procedure in B to allow for this. We can say calculate A equal this one, P. A is P minus 50. Okay, P is same as P minus 50, minus 5. P minus 5 and B is equal, remember 50 here, okay, is the position of the center of mass. In this case, it is 48.7. Okay, so now we calculate B as 48.7 minus P. Okay, this is the change that we need to make. A student investigates a circuit containing different combinations of resistors. She uses circuit A shown in figure 2.1. Circuit A is not yet complete. It's not a complete circuit. On figure 2.1, complete the circuit to show a voltmeter connected to measure the potential difference across the resistor U. So we need to measure the potential difference across U. We all know that to use a voltmeter, we need to connect it in parallel. Okay, so this is our voltmeter. As the student measures the potential difference PD V across resistor U and the current I in the circuit. So he's measuring V and I. So read and record in table 1 the values of V and I shown in the meters. So if we come here, you can check that the small scale mark on the voltmeter is zero point 0.1 volts. Okay, how did we do that? Between 0 and 1, there are 10 scale marks, then 1 volt divide 10, it is going to give us zero point 0.1 volts. Okay, so the measurement here is 1.567. It is 1.7 volts. Please make sure to understand and practice how you can measure or take the reading of an analog scale, like a voltmeter and an ammeter. Okay, for this scale, the smallest scale mark is 0.02. How did we do that? From 0 to here is 0.2. It got 10 scales or scale marks, then 0.2 divide 10, it is 0.02. Now we have 0.4. Okay, the next scale mark is going to be 0.42. Okay, now we calculate the resistance. The resistance is simply V over I. Most of the time he's giving us this recommendation. R, okay, okay. Now use the relation from table, readings from table 2.1 and the equation R is equal to V over I to calculate the resistance R for each combination of the resistors. So we have to use this equation to calculate the resistance column. Okay, then it is 1.7 divide 0.42, 4.045. 4.05. If I just follow the equation again and do the math, then I get 3.89 and I get 3.81. Okay? Please check for yourself. Okay? Now, a student suggests that the values of R should be the same. This is a student suggestion that all the values of R are the same. State whether your results support this suggestion. Justify your statement by reference to the values from the table. Okay? Now, this is how we do it. In the case that you are given two values or more than two values, and you were asked to say if they are equal or not, or you think they are equal or not, this is the way to do it. Okay? Calculate this value. Calculate this value. Maximum minus minimum, divide by the minimum and multiply by 100. If you have two values or more than two values, okay, and you were asked to check if these values can be considered to be equal or not, this is how to do it. We take the maximum value minus the minimum value, divide by the minimum and multiply by the 100. Now let us check. The maximum is 4.05. Minimum is 3.81. Okay? Then we apply the equation. 4.05 minus 3.81 divide by 3.81 multiply by 100. Okay? 4.05 minus 3.81 divide by 3.81 and multiply by 100. Get 6.3. So what should we do with this value? If this value is less or equal than 10%, okay, then we can consider the values, okay, or the bunch of values to be equal. If this value comes to be more than 10%, okay, then the values cannot be considered as equal within experimental limits. So in this case, the values or the all the values are within 6.3% of each other. Okay, so we can consider them to be equal within experimental limits. So the statement, yes, they can be considered equal. Why is that? They are approximately 6% within each other. That is to say, within the allowed experimental limits of less or equal 10%. Okay, this is the way to do it. If you are given two or more values and you were asked to calculate whether these values are equal or can be considered equal or not, the way to do it is calculate this value, maximum minus minimum, divide minimum by 100. If it is 10% or less, then you consider them to be equal within experimental limits. If they are more than that, then no, they cannot be considered equal within experimental limits. Please remember this method, because in most of the exams, you get a question of this form. A student determines the resistance of resistor R using a variable resistor to control the circuit. Complete the circuit in figure 2.6 to show a variable resistor, okay, used for this purpose. Remember, a variable resistor is the one that we use in a circuit to vary the resistance and hence vary the current within a circuit. This is the symbol for a variable resistor. So we draw it like this. We draw it like this. Like this. And like this. Okay? Brief explain one advantage of using a variable resistance to determine the resistance rather than the procedure carried out. It allows us to vary the current in the circuit much easier and allow a wide range of readings. Okay. A student suggests that the potential difference and the curve are proportional. State how a graph of potential difference against current for the resistors can be confirmed this. So, for two values to be proportional, two values to be proportional, okay, it need to be a straight line. To be a straight line passing through the origin, meaning the graph plot or the plot of V and I need to look something like this. a straight line going through the origin. So we say the graph plot of V and U, and I would be that of a straight line. The line need to pass through the origin. What is origin is 0, 0. Okay? So remember, if you are told two values are proportional, okay, meaning that if you make a plot or a graph plot for those two values, you get a straight line, okay, and the line should pass through the origin, okay. Now you come to question number 3, okay, and typically these kind of questions is just to follow instructions. So what does it say? The student places two mirrors, FE and FG, at an angle of 100 degrees to each other, as shown in figure 3.1. So we have two mirrors, and they are at an angle of 100 degrees to each other. On figure 3.1, draw a normal to FG at point N. Extend the normal below FG, label the lower end of the normal with the letter G. So we need to draw a normal to the mirror FG at point N. FG and point N. So we have FG and point N. What does a normal means? A normal means a line perpendicular to a surface. So two lines are perpendicular, or one line is normal to another if the line makes an angle of 90 degrees. So use your protractor and draw a line which is 90 degrees to FG at point N, like this. Okay, label it. What should we label it? Label the lower end of the normal with the letter L. Let me see. L. Okay. The student draws line AN as shown in figure 3.1. So he draw line AN, this one. As shown. On figure 3.1, measures the acute angle theta 1 between the line AN and GN. So we need to measure the acute angle, which is the angle less than 90 degrees between AN and GN. So this is AN and GN. So he's also kindly marked. So use your protractor to do that. Okay, I measured that angle and it turned out to be 15 degrees, and we got the units over here. The student places two pins P1 and P2 on the line AN as shown in figure 3.1. Measure the distance D between pins P1 and P2. So you measure this distance. Use your meter ruler to measure the distance between P1 and P2. I did that and it came up as 3.5 centimeter. Now suggest whether the two pins are a suitable distance apart or not. Okay, the recommendation for the distance between any two pins for this kind of experiments, they should be at least 5 centimeters. Okay, this is the recommendation. The two pins should be at least 5 centimeters apart. In this case, the student used 3.5 centimeters. Are they good enough? No. No. explaining why the two pins need to be at least 5 centimeters apart. The student views the image of P1 and P2 in mirror FE. Okay, if the image of this is going to see them on this mirror FE. Okay. She places two pins, P3, P4, so that pins P3, P4, and the images of P1 and P2 all appear one behind the other. Draw a line through P3 and P4, extend the line 10 centimeter above FE. So he is asking us to draw through pin P3 and P4 and extend it 10 centimeter above. So this how the line looks like. Okay, this is the line going through P3 and P4 and extended above approximately 10 centimeter. Now, so we are done with this part. Label the upper end of this line as R and B. This is B. And should we say it is R here? Okay, we are done with this part. The student repeats the procedure for an angle theta 2 is equal to 40. She places two pins P5 and P6 so that P5 and P6 and the image P1 all appear one behind another. So he repeating for P5 and P6. Okay, good. Draw a line through P5, P6, extend the line until it crosses BR. Label the upper end of this line with T and C. Okay. So again, we are going to draw a line. Okay. And we are going to label the line as what? C and T. Okay. This is C. And we are labeling it here as T. Okay. So we have followed all the instructions as instructed. Measure the acute angle alpha between BR and CT. So where is this angle? Between BR and CT. If we look carefully, this is the line BR and this is the line CT. So this is the angle alpha. Okay. We do measure that with the protractor and I get a value of 27 degrees. 27 degrees. Okay. A student thinks that there is a relation between the angle alpha and the value of theta 1. He thinks that there is a relation between the angle alpha and the angle theta 1. State what your results suggest that relation could be. Justify your answer by reference to values from your result. So what should we do? Let us report theta 1 is equal. Let us write it. What is theta 1? Theta 1 is 15. What is theta 2? Theta 1, okay, and theta 2. Where is theta 2? Where did we calculate alpha? Alpha is equal to 27. Theta 1 is 15. Where is theta 2 mentioned? Oh, theta 2 is here. Theta 2 is 40. So it is not kind of straightforward to see a relation. But if you look a little bit closer, okay, if you calculate theta 2 minus theta 1, okay, it is 40 minus 15. It is 25. Okay, so maybe it is the relation between them is statement alpha is equal theta 2 minus theta 1. Okay, alpha is equal theta 2 minus theta 1. Alpha is 27. Theta 2 minus is equal 25, or sorry, let me write it like this. Alpha is equal theta 2 minus theta 1. Theta alpha is equal to 27 degree. Theta 2 minus theta 1 is equal to 25 degree. Can we check if they are equal or not? Okay, then we calculate maximum minus minimum, divide minimum by 100. So maximum is 27 minus 25, divide 25 by 100. This is 4, 2, this is 8%. Okay, then we can say they can be considered equal within experimental limits, less or equal 10%. Okay, suggest 2 precautions to take in this type of experiment to ensure accurate results. Okay, ensure pins are at least 5 centimeters apart. Okay, observe basis of pins, meaning when you are carrying out the experiment, when you are trying to align the pins one after the other, okay, do not look at the top of the pins. Always try to look at the bases of the pins. Okay, we can add another one. Maybe you can use it instead of these ones. Okay, use thin lines. So I guess one reason why different students all doing this experiment carefully may not obtain identical results. Why we cannot get identical results even if we try to carry out the experiment? The reason is very simple. Okay, it is always very difficult to decide if a number of pins are exactly behind each other. Okay, so we can say difficulty to align pins exactly one behind the other. That's simple. Okay, I think we are done with this question number 3. Let us go with question number 4. And this is the investigation question. Okay, A student investigates the rate of cooling of hot water in a container which has a lid. Plan an experiment which will enable him to compare the effect of lids of different thicknesses on the rate of cooling. The apparatus available: a beaker, a supply of hot water, insulating material from which lids can be cut. List any additional apparatus needed. Explain briefly how to do the experiment. Include the measurement to take. Okay. So what else we need? We are going to need a thermometer, a stop watch. Okay. In this kind of experiment, as you all know, we have to decide which one is the independent variable and which is the dependent variable. The independent variable, okay, is the one that we can control ourselves. It is the one that we choose. In this experiment, he's telling us we need to investigate the effect of lids of different thicknesses. So the thickness of the lids need to be the independent variable. Okay. Now, the dependent variable is the one that we are going to calculate or measure. In this case, he's asking us about the rate of cooling. Okay. Can we actually measure the rate of cooling directly? No, we cannot actually directly or have a measuring instrument to measure the rate of cooling directly. So what we are going to do, we are going to heat the water to a certain temperature, allow it to cool for a certain time that we choose, for example, 10 minutes, okay? And then we are going to calculate the drop of temperature in this time. The change in temperature divided by the time gives us the rate of cooling, okay? Then we repeat the experiment again with the lid or with different thickness. Again, we heat to the same initial temperature, we allow it to cool for a certain time, we measure the new temperature, calculate the rate in cool, and repeat for a number of times. Okay, we report our values in a table. What we need to keep constant throughout the experiment, we need to make sure that we are using insulation or lids made of the same material. We need to always use the same amount of water, or volume of water. Make sure to use the same type of beakers. Make sure always to cool the temperature, to cool the water for a fixed amount of time. We don't do it for 10 minutes and then we do it for 20 minutes to make our comparison easier to compare. Okay, and we make sure that we keep the room temperature constant throughout the investigation. So let us try and write this. First, we have to draw the diagram that we, or the setup that we are going to use. So we have a beaker. Okay, we have a thermometer. We have a lid. Okay, this is the thermometer. This is the water. Hot water. Thermometer. Lid of thickness D. Okay, so this is our setup. Now we tell him arrange the experiment as shown. Okay, using a water heater, heat the water to a temperature larger than theta I. Okay, so we are going to set the initial temperature when we are going to start timing as theta I. Okay, what we are going to do first, we are going to heat the water to a higher temperature, a little bit higher. Then we are going to transfer the water. We are going to transfer the water to the beaker, set the thermometer, close the lid, and just wait for the water temperature to drop to theta I. Then we can start timing. Pour a volume V of the hot water in the beaker. Cover with the lid and use a thermometer to measure the water temperature. When the or start the stop watch when the water temperature drops to theta I. Stop the stop watch when the water stop allow the water to cool for a fixed time between two brackets. You can say 10 minutes. Okay, then measure the temperature theta F. Tabulate the readings in the table below. This is our table. We forgot to say measure the thickness of the lid. Okay, D degree centigrade, sorry, centimeter. Okay, theta final degree centigrade, and here R is the rate of cooling. R is theta initial minus theta final divided by the time T. Okay, this is the rate R, rate of cooling. We can say here, use a vernier caliper to measure the diameter or the thickness of the lid. Repeat the same procedure with lids of different thicknesses. Okay, make sure to use the same volume of water in each experiment. Keep theta I and T the same throughout the experiment. Okay, keep the room temperature constant. Finally, make a graph plot of D on the x-axis and R y-axis to investigate the relation between D and R. Okay, I think by this we have answered this question in full. Okay, I hope that was useful for you, and see you next time. Cheers.